Okay, we're talking about fatigue testing in this lab, and this is a little bit of a lecture to get you prepared for the lab. And when we think of fatigue testing, it is a cyclic loading that is under the yield strength. Okay, so this is not where we're plastically deforming the material, we're elastically deforming it. So we wouldn't expect it to break under one cycle of operation. Now, when we do a cyclic loading, for example, we may want to push down on a member, putting the top portion in compression and the bottom portion in tensile on a simply supported piece of material here. And then let's do a symmetrical loading where we push the other way, the same amount of deflection, and we reverse the tensile and compressive forces that we're going to see on the beam. Now, if we were to plot this out over time, we would see positive and negative forces being applied to this sample. Now, this is stress and this is time. We have two different types of loading and plots that we can generate here. Again, before we get into this, the two types, let's look at this beam right here. We're holding it fixtured here, and we can come over here and we can bend it up and we can bend it down. If that delta, the change from here to here, is the same on the up and the downward stroke, then it is going to be symmetrical. And so we would expect to see a nice symmetrical plot like this. Now this is nice, and the kind of loading that we're going to do in lab is going to be symmetrical loading, and it's going to be constant rate. In real life, you're probably going to see a variable application of the loading. It's not going to be a cyclic. So this is going to be a really good experiment to prove under a symmetrical cyclic load what's happening. Now here we have an asymmetrical where about the zero we're loading more in one direction than we are the other direction, and we're continually doing that. One of the things I want to point out here is if we're doing symmetrical loading, I'm probably going to stress the top portions of the fibers because this thing's not rotating, even though it shows a round member, it could be a square. If I'm coming in here, I'm probably putting my stresses higher on the outer surfaces here, and that's where I'm going to tend to break. Now we see these nice curve marks here. We typically refer to those as what we call beach marks. This is our fracture zone. If it's symmetrical, typically that fracture zone will be centrally located between the origin and these radiating beach marks, just like here. Compared to asymmetrical, you notice it's pushed down one way more than the other because it was loaded heavier one direction than the other. So we see this fracture zone moving downward. So that's something you want to look for when you guys look at your failures is where's my fracture zone on there? Looking at fracture zones, now these pictures that we're looking at on this slide are non-rotating members. Again, they're just kind of like this reed or this piece of material that was put out here going up and down, and we can consider these plane bending. Now plane bending is where we're coming in here, maybe just pushing down and coming back, pushing down and coming back. Reverse bending is where we're doing it both ways. We're coming up and down, up and down, up and down. And that's going to be like one of your experiments that you're going to do on the little green machine. Now, when we look at this, if I'm just going bending back and forth, you're going to have low stresses, high stress concentrations. We could see ratchet marks. See these lines that are kind of radiating out up here? This is an example of this one where we have these ratchet marks. Then we have our progressive beach marks coming, and then our fracture here. Typically, you're going to see an origin start somewhere and then it radiating across. Again, reverse two-way loading. We're expecting to see, as long as we have a symmetrical load, that it's in the fracture zone is in the center, and we may see ratchet marks on both sides here. Now, if you look at this broken part over here, this would be an example of this right here. We see some small ratchet marks here, see some bigger ones here because it actually started to break here, and then we're not symmetrically loading here. Here's that final fracture zone right here that happened. So this wasn't a true symmetrical failure here. Now in this slide, some more failures. These are rotating, okay? These are rotating. And if I had an example, let's look at this first one right here, and it's rotating clockwise. If I had a stress concentration, such as a key or maybe a nick in the shaft, and it started to fatigue because the stress is always going to be the highest on the most furthest out portion of that shaft, I'm going to see it starting to fatigue there and then beach marks radiating out and then eventually breaking. So this is an example of that kind of shaft where it started to break here, beach marked out, and then failed. Now, what are we going to do in lab? Our failure should look more like this because you're doing low stress, high concentrations all around, even loading. And what we're going to see are, again, these telltale signs of ratchet marks. Now, they may not be as long or as pronounced at this, but you're going to have to look at them very closely. And we should expect to see ratchet marks from stresses building. We'll talk about how that works here in a minute. And then eventually breaking with the fracture zone in the center. So we really can't tell what direction this was rotating like we can on this type of failure. Let's talk about the cracks propagating and how they grow. Again, imagine a lot of time happening here and a lot of time happening when we talk about this. If I load something, pull it in tensile and release it, and pull it in tensile and release it, eventually I'm going to get a small imperfection in the material. And it's much like these pictures show here. The atoms are nice and happy and the stresses are going to be high out there. And on that surface, what's going to happen is I'm going to localize work some of the bonds here, and it's going to slowly break down and make a little imperfection that's going to let me yield and break that material here over time. So every time I end up loading it, it's going to grow and propagate across here till eventually I get that fractured surface happening there. So here we have our cyclic positive stress being applied. It's going to open that up. Now again, imagine it's taking a lot of cycles to do this. We're just doing it in 3 or 4 cycles here. And then as we go back to a compression, it's going to compress that together, come back up, it's going to open it more and down and up. Now may take hundreds of thousands of, or even millions of cycles to make this happen here. Okay, I see a lot of people talk about fatigue and use a paper clip for fatigue. And I wanted to throw this in here because we're doing fatigue below the yield strength. A lot of people will use a paper clip in fatigue and they're actually plastically deforming the material here. They'll hold this out here, straighten this out, and then they'll bend this back and forth until it breaks. The problem is we're putting so much stress on there. It's such a high stress value that we're actually plastically deforming, and it's going to be considered a very low cycle form of fatigue. We're going to be doing higher cycles of fatigue in this class. And so when we think about this, we need to think about the stress strain diagram. Here's our yield point. We're going to be functioning in this elastic range for our labs. So you're going to be working in the elastic range where we have the rise and the run, the modulus elasticity. So you're going to have to go to MATLAB and look up your modulus elasticities for your materials that you're using in this lab. And we're going to be calculating the stresses in this area from that. Now then, this is a introduction to what we call SN curves. S meaning stress. I know I'm showing load here, but we take the area and the loads and we can calculate stress in this column right here. Down here we're going to have typically a log scale showing the number of cycles. So S represents stress, N represents number of cycles, SN curve. Now, if I don't have very many cycles, I'm going to have static failure. I can bend it and just break it, okay? I'm going to have what we call a low cycle failure that's going to happen here. This is still going to be some high stresses, but I'm going to be able to cycle it. You guys are probably going to be down here in this high cycle range in this lab where we're putting very low stresses and we're going to fatigue it under a large amount of cycles, okay? Some materials have a phenomenon where we can hit fatigue endurance limit. That means your steels are really like this. I could hit a lower stress value and I can load it almost infinite cycles and it will never break because the stress is just not high enough. Some of our aluminums won't have that phenomenon happening there. So we're going to see this in the different diagrams. Again, this is an introduction to SN diagrams. Here's a SN diagram that's been plotted off of experimental data with all these dots being taken at different stress levels, and then they can draw a line trajectory through here, labeling things like low cycles, high cycles, our infinite length. This is our SE. This is going to be our fatigue limit right here. And a lot of times we'll take the ultimate tensile strength of the material times 0.5 and establish that stress level being that for the steel samples. And this represents infinite length happening here. The other thing I want to point out on this is we have our number of cycles down here and our fatigue strength here. This is a log scale, and you're going to have to read how many lines, and really each chart's different. You're going to have to figure out what the value of each line in the divisions are between the major number of cycles there on that log scale. One of the things we want to point out is you're going to have the ability to take a class like Machine Elements, machine design, some schools call it. It's basically a course that's going to take you through, a lot of schools use a Shigley's book, and they're going to go through a lot more to this fatigue testing. This is just a good introduction lab for this. Things like the condition of the material. Was it a Roth shape that we're testing? Is this something that's bar stock, that was hot rolled, okay, or cold rolled type materials? Or was it something that was sand cast out of that same alloy? Depending on how it was manufactured, I'm going to see different factors coming into play in terms of the number of cycles that we're going to be able to have this material work. So looking at factors, we can have factors that relate to the surface finish of this part. Is it polished? Is it ground? Was it machined? At what machine level in the finish? Was it hot rolled or forged? We can look at the different K factors for those surfaces, and that's going to change our strength capabilities for the number of cycles. Likewise, is this part a 2-inch diameter or a 1/4-inch diameter part? We're going to have size factors, loading factors, temperature factors, reliability factors. That's stuff you are going to cover probably in later courses. We're not going to be applying any of these factors at this time for this experiment. All right, let's take it to the next level of where we're headed with this lab. Anytime we take something and bend it, we already talked about the top portion could be in compression and the other portion being in tensile, and we're going to do that cyclic loading on that piece of material. And when we do that, we're going to see the maximum stresses being applied to the top portion or the most outer portion of that material, whether it's in tensile or compression. And so we're cycling it through that. We're going to see this neutral axis develop. That neutral axis kind of represents were we symmetrical or asymmetrical and how we loaded that. Now then, if I take a kind of a quick stab back to statics, you guys are used to seeing things like a simply supported beam. We have a load on it. Now this is not centrally loaded here. It's 6 inches versus 4 inches, but somewhere in this beam, we're going to, if we just kind of broke and cut that, we're going to have some internal forces. This beam is going to want to bend down. The top portion is going to be in compression. The bottom portion is going to be in tensile, and there's going to be internal forces there. Now an I-beam has the most material out there where the high stresses are. That's how it's designed. Where that neutral axis, there's not as much material needed and required because that's not utilizing the material where the stresses are. We can take it one step further, and you guys remember that we could calculate the internal shear forces and the resulting bending moment. Boy, this is going to be huge. We need to calculate these bending moments, especially for the rotational bending problem that we're going to do. So what we're going to work on right now is stuff that's going to help you for the rotational bending portion of the lab. So what you probably need to do is get out your good old engineering paper and put given, find, and solution. Now this is real symbolic to what you're doing with that sample, where you're going to have a force here and a force here. Now we only have one force being applied here. You guys are going to put 2 forces on there, and you're going to have to measure how and calculate the forces you're loading it with. What are the dimensions relative to everything that I'm loading? We'll talk about that here in a minute. And I'm going to have to calculate my reactional forces here. And the ultimate goal is, what is my bending moment here for this? So to do this, I need to do our beam diagrams. And the first thing I'm going to do is draw a free body diagram. That means I'm going to label the forces on here that react, representing the simply supported beam. We know AX is going to be 0 because there's no forces in the X direction being applied. Now I'm going to come in here and sum the moments about A. And I put this as a hint. If I'm summing the moments about A, this 500 pounds about A is trying to go clockwise right here. See that hint? Clockwise is a negative moment. So negative 4 foot times 500. The B is trying to go counterclockwise right here, which is a positive. So that's positive 10 feet times BY. Solve for BY. I've got it. Again, you guys in your lab, you're just going to have another force right here, and you're going to have another little piece of math here for that. Now then, I want to come in here and solve for the reaction at AY. Since I know the load, my BY, I can just solve the the forces about y, which is going to be sum of the forces about y, which is 0, and I can come in there and calculate my AY. This should all be reviewed for you guys. Now then, I need to draw a shear force and a bending moment diagram. This is the one I really want to know because I want to know where the maximum bending moment is on that beam. So first thing I have to do is I have to draw my first order curve here off of shear, and that's going to be forces. So we had a 300 pounds at AY. We're going to go up. Nothing happens for 4 foot. We're going to come down. We had a 500 pound load, come down 500 pounds. Nothing happens for the next 6 foot till we get over here, and we had a 200 pound that took us back to 0. So we have positive, negative areas here. If I take that area, the 4 foot times that 300 gives me 1,200 foot-pounds. That means from here to the point here, and you need to draw this with a ruler to scale. You're going to have to turn this into as an attachment as part of your lab. You're going to come in here and label the 1,200. Draw this line. This is the next order curves. If I went to the next order for deflection, it'd be parabolic. What I'm going to do is come down here, negative 1,200, back to 0. So this is my maximum moment right here that I have for that. So I could put that into an equation. Now, what equation would I want to put that into? Well, let's get some more data, and we'll talk about that equation here in a minute. One thing I need to know is the property of that material. The material that we're testing is round. This is for the rotational bending test. That's this sample right here. And that diameter is going to have a cross-sectional property called the moment of inertia, which is pi d4 over 64. We're going to calculate that I value. Now I'm going to bring this up here, and we do have a bending stress calculation. Remember, we wanted that moment, the I. We have those. Let's go ahead and look at this real quick while we're on this topic. We have the bending moment. We have the I value. C is the radius of the shaft. We could calculate our bending stress. Now, I want to point out some stuff on this picture that I've put up here for you. This is similar to the sample that you're going to have in the aspects that you're going to measure the diameter, and it's probably going to be close to 0.3 on your sample. The other things you're going to need to measure is how far is it from this force to this force. This is the force that is going to be located about the pivoting point right there relative to this pivoting point. So you need to take and measure that. So you're going to measure that point, and then what you're going to measure it from here to here and capture that distance. Now, on the sample, close to the collet sides, we're going to have 2 cables coming off, and we're going to be pulling that sample. And we're going to put, I believe, 65 pounds force for your lab. Check the lab sheet to see if we change it from semester to semester. But if I put 65 pounds, then this is half, and this is half of 65. I can solve for these reactional forces. I'm going to need to measure the distance from the pivoting point to where I'm putting that load on. And I'm going to do my statics. I'm going to calculate my bending shear and my bending moment. And now that I have the I value for that, I can calculate that stress value. Okay, so that's how we do the calculations for the stress on that one. You're also going to do another fatigue sample using a flat specimen, and it's called a Krauss fatigue sample. And this one's a little bit different because it's not so much that it's a nice rectangular shape. We have this cone shape that's coming off about this point right here, and it's going to put a fracture zone in this sample right here. So we're going to have an equation for it for calculating the stress. And what we need to know are some things from this diagram right here. We're going to need to know the length. So you're going to measure your part from here to here, which should be close to the nominal dimension of 2.5 inches. We're going to need to measure the thickness of your sample, so length and T. And what we're going to do is come down here and use this equation right here for calculating the stress. We're going to need to know the deflection. This delta is our deflection. And what you're going to do is when the beam is flat, we're going to zero out and measure with the dial indicator. We're going to come in and raise the beam up, turning the wheel by hand with the machine unplugged. And we're going to see that the maximum deflection is going to be held. We're going to do a symmetrical load in this course. So really no need to measure the bottom because we've got it set at 1 and it's going to do a symmetrical load up and down here. So our deflection is from here up. That's our deflection. E, that's our modulus elasticity. Go to MATWEB, look up the properties for 2024 T4 aluminum. We're going to use that same aluminum on both samples, so it's apples and apples here. And then the thickness is what you're going to measure and your length, and you can calculate the stress values. Now in both cases, we've calculated the stress that we're going to use on this experiment. And here is the SN curve for 2024 T4 aluminum. So again, the stress, and here we have KSI, here we have it in megapascals. Here we have the number of cycles, so SN, we know what the axes are, and this is for aluminum 2024. Now there's actually two different types of samples that can be had. One is notched, and this is the experimental data and their rough plot here. We're not going to use this portion. We're going to use this portion up here where they're using a smooth sample because our samples are fairly smooth, and we're going to use data right up in here off of this plot. So somewhere in this range is what we're wanting to look for. We calculate our stress. So if I calculated, let's say 35 KSI, I would come over here, and then I maybe come down here and go 10 to the 6th power there. So I can kind of start estimating how many cycles I'm going to get out of this. Now if I'm running at RPMs, I can take the RPMs and those cycles and figure out how many times it's going to take to break. I can actually figure out the time that it's going to break at that. Or if I'm going up and down at a certain number of cycles, I can do that as well. So you're going to read your lab sheets and apply that and calculate the number of cycles till failure on those samples and compare to what really happened. So I hope that helps you out, and we'll catch you in lab.